We're sticking with light and what light does when it hits various surfaces. So we're interested in what happens when light waves go from one kind of medium to another. What kind of waves are light waves, Kylan? Okay, so light waves are electromagnetic. What do we know about electromagnetic waves, Andrew? Okay, so they can travel in a vacuum. How? What do you know about their travel in a vacuum? Which is? Okay, so 3.0 times 10 to the 8th, and then meters per second. Correct. All right, so Jordan, what happens to light waves when they go from air or a vacuum into some other medium? The speed decreases? Yes. Okay, so going, and any medium compared to a vacuum is going to be what in terms of density? More dense, less dense? More or less dense? More dense. So going to more dense mediums, speed decreases. This is review, right? Nothing new so far. So let's take an object, and when we draw diagrams, we tend to use arrows as our object. Why? They're easy to draw, so you don't have to be an artist. They show directionality. If I just drew a line, I wouldn't be able to tell if the line was right side up or upside down. If I have an arrow, that's easier to see. I also am going to, when I draw objects, have them sitting on some sort of reference. Just like I had that reference line with sound, that principal axis or reference axis with sound, I'm going to have the same thing when I'm drawing light diagrams. So this is my object, and we're going to show not light waves, but show the direction in which the light waves are traveling, and we're going to represent those using light rays. So an arrow is going to be a light ray, and it shows the direction of travel. Aaron, do you remember how the wave fronts are going to be oriented relative to the direction of travel? Perfect. The perpendicular wave front compared to the direction of wave travel. And so we're going to be working with light rays. Light rays travel in what kind of direction, would you say, Eric? For instance, the light from the ceiling light there is traveling how to get from it to you? Okay, we talked about sound waves traveling wave fronts in case of sound as spheres. We're talking about light rays. So how would, if this is my light bulb, do I have light waves coming out like this? Like straight. Okay, so light rays travel in straight lines. Is that what you're trying to tell me? Okay, you're correct. So light travels in straight lines. Is that important, Kylan? Yeah. How can you tell? Yeah. I put a star by it. So yeah, light traveling in straight lines is a really important big picture idea. So I've got light going in straight lines. If I have an object, so here's my object, light rays are going to be emanating from all parts of the object in all directions. So I'm going to take my light rays in all directions from all parts of the object. Light rays from object projected in all directions. Now I can fit it in. It's a pain in the neck to draw all those light rays. We're not going to do that. We're going to focus on light rays, 1 or 2, maybe 3 light rays from each end of our object. That makes it a lot easier when we're dealing with these things. So we'll draw our object again. The reason we're going to pick light rays from each end is if we can see light rays from each end, then we can see each end of the object, and that means we can see everything in between. Does that make sense? Narisha, I'm sorry. So here's an object, a little bit more classy than an arrow. And so here are all the various, or not all of, but a handful of the light rays being projected in straight lines from the tip of the tree, right here. And then same thing, here's the other end of the tree at the base of the tree, and here are all of our light rays projected there. Some of them are going to intersect, some of them are not. So this one's not intersecting. All right, and all those light rays, if they hit a screen, can create an image. Today what you're going to do for the lab, you're going to use a pinhole camera. Pinhole camera is essentially the very basic principle of how a camera works. And what we're going to try and do with this pinhole camera is to see how light rays travel and how images are made on a screen with our camera. So your tools are really high class. The bottom of the box has been sealed, and there's a, depending on how your box is oriented, you can kind of tell there's a seam that runs here, and there's a gap in the seam. So if you look through the lab, it tells you that you're going to create a hole, and the dot on your lab sheet is about how big your hole needs to be. So using a pencil or a pen tip, start with a little hole. You are going to position your box so that the bottom of it is aimed straight at the lamp. And if you look, you're going to be either near the lamp or far away from the lamp, and you're going to trade off positions. So near the lamp would be about how far away Lexi is. Far away from the lamp would be the table behind Eric, so about 3 rows back. I have 2 lamps. So 4 of you are going to work with this lamp, 2 starting in front, 2 starting back, and then when you're done, you're going to switch positions. Because if you take a look, number 3 and number 5, you're recording the object distance. This is going to be your object, so it's a letter F. Why do you suppose I picked F instead of A or K or M or something like that? Yeah, so I can see if it's oriented left or right. Any other ways that I might want to, I could do that if I picked E or B. Perfect, you see upside down. So F is one of the only 2 or 3 letters where you can tell left or right orientation, and you can tell upside down, right side up orientation, all right? What we're trying to do again is to look to see when the light rays come through this pinhole and hit the screen. Inside your box you have 2 tools. You have a ruler, and that's going to allow you to figure out how far is the screen from the pinhole. All right, and your screen is this translucent sheet of paper, and so you're going to position it vertically. It doesn't matter whether it's the shiny side or the smooth or the kind of rough side that faces the pinhole. You're going to get an image either way, and your job is to figure out where you want this. I'd say about halfway to 3/4 of the way back from the pinhole would be where you'd want to position this. And you want in number 1, or activity number 1 rather, you want your screen to stay at the same position pretty much. Because then in activity 2 you're going to stay in the same position relative to the object. So your object distance isn't going to change. Your image distance, you're going to move the screen. Does that make sense? So we're looking at, if I keep the screen in one position for activity 1 and change how far I am from the object, what happens to my image? If I stay a fixed distance from the screen, so my object distance is constant, that's activity 2, and I move my screen so my image distance changes, then that's what I'm looking at. And then in activity 3, if you flip to the next page, you're increasing the number of holes. So you're going to make the hole you have slightly larger, and you're going to look and see, okay, now I've got a bigger hole, what happens to my image? The things that we're looking at for image is size, sharpness or clarity versus blurriness and fuzziness, and brightness. So what happens to those 3 things, the size, the clarity, the brightness, as I change positions, as I change hole size? Pretty much all of it. You want to be as straight on as you can be. So that means that when you are doing activity 1, activity 2, etc., you're going to be at the same table as the other person. Though there's a tape measure set up back there, I'll set up a tape measure here and pull it back so you can see to the nearest, let's say the nearest 1/10 of a meter, what your object distance is, and to the nearest centimeter for your image distance. Yes, I want this in your lab notebook.